Hey, how's everybody doing? Welcome back to the Math for Healthcare video lecture series. And here we are on Unit 1B, and we're going to look at applications of exponential and logarithmic functions. Some of those applications are going to involve using what we learned about solving exponential equations as well. And I do want to say I'm going to go over these, but if you want to look for more examples, in the textbook, the business pre-calculus textbook, there's some great examples here of these in the exponential and logarithmic modeling section. Okay? All right, so let's review here. Here's an application, and we looked at it a couple of lectures ago, and it's kind of what sent us on the path to using logarithms to solve exponential equations, right? So here we had the example depositing $2,500 into an account that compounds continuously with 3% interest. So what I want you to try on your own, what is that function? So x, we have our initial amount, 2,500, because it's continuously it's base e and 0.03 x. Okay. Now, recall we had this issue is we want to know here in this first one, we wanted to figure out, by the way, that is graphed in the bottom left corner of the screen there if you want to look at that function f. Now, how long will it take the balance to reach $10,000? All right, so basically we're asking, when does f of x reach $10,000? Remember, and f of x is equal to 2,500 e to the 0.03x. So same thing. When does that reach $10,000? All right. Well, we saw we could do a little work down here, and we know we could divide both sides by 2,500. We'll check that again by the is 4. Okay. So we get 4 equal to e to the 0.03x, right? Now, this is where we stopped. But now we know from last time, what do? We got the variable stuck in the exponent, so we take a log, correct? Both sides, natural log of 4 and natural log of e. And we end up with natural log of 4 over on the right side there. The natural log undoes e. Another way to think about that is this is 0.03x. And if you're unsure of that, be sure to revisit the video from last time why that happens. So that we get x equal to the natural log of 4 over 0.03, which is approximately, let's go over here and check it out, ln 4 divided by 0.03. That turns out to be approximately 46 years. And I should write that years, right? Years. It's important. Take 46 years to reach 10,000. All right. Now, we could check that. Look, plug in f of 46. I should pretty close to 10,000. Okay. Now, let's erase that work there. I'm going to write this as approximately 46 years. All right. Now, how about this next one? Well, we've got the same equation, except for now we want to know when that function is 7,500. So we have 7,500 equals 2500 e to the 0.03x. Alright, so here we need to do 7500 divided by, and that's 3. Okay. Okay. So 3 equal to e to the 0.03x. We take the natural log of both sides, and we get, I'm going to do this one a little quickly, but same steps as before, and we end up with x equal to natural log of 3 divided by 0.03, and that equals what? Remember, we could just calculate the natural log of 3 divided by 0.03. And let's call that about 36 and a half years. So 36.5, and that's approximately. Alright, let's get rid of this, and we'll write down, before I forget it, approximately 36 and a half years to reach 7,500. Okay. Now, lastly, how about 5,000? Notice this is going to be how. There's another way to ask this is. We can write down our algebra 5,000 equal to 2,500 e to the 0.03x, and this is going to be how long would it take for your money to double? All right, so we divide and we get 2 equal to e to the 0.03x. We're going to use our natural log of both sides to get that variable out of the exponent. Alright, and we end up with x. Again, I'm going to make this a little short here, but x equal to the natural log of 2 divided by 0.03, and that is approximately, number to 2. Okay. 23.1. Okay. So notice what do we want to notice here? So let's get rid of this work so it's out of our way. We have now, how long did it take to double? About 23 years. Okay, so let's see. So it took notice it took 13 years to go from 5,000 to $7,500 in the account. Okay, that's a difference of 2,500. That first difference of 2,500 took 23 years. All right. So what is this telling me? Well, it's increasing quicker the further out I go. Unlike a line where it would be exactly the same. If it took 23 years to get to 5,000, it would take another 23 years after that to get to the 7,500. And that's, again, a big difference with ours, with exponential functions compared to linear. Okay, so that's our example. That's how we're going to use solving logs, and now we have that ability, and really opens up the number of problems we could do, the application problems. Okay, so some more applied examples. Why do we use them? Again, it's a reminder. Many physical quantities are best modeled with exponential functions, for instance, unconstrained populations, radioactive decay, interest, and drugs leaving the body, and obviously a bunch more. Now, measurements sometimes are made on a logarithmic scale. The Richter scale, the pH, and the intensity of sound are ones for that. Now, you may ask, why would we do that? So, why here? Well, sound, okay, goes from 20 decibels, 20 micropascals ranges to 2 billion. 2 billion pascals. Okay. Well, what does that mean? Why do we care about that? It's such there's such a range of numbers there. They're different by orders of magnitude. So this way, we could think of it if we take log of our sound measurement. It could be anywhere from basically 1.2 or something up to now 2 billion. All right. Well, what is that going to be when I take the log of 2 billion? It's going to be somewhere about the log of a billion, which is 9 in log scale. All right, so it's when we have this big range of numbers, we want to put we take the logarithm of it so that it makes it more manageable. Maybe here I'll show you here with the sound some differences, and these are all things that are audible and see, but here's my list up here. 20, I take the log of it. Okay, so it goes from 1.3 to 9.3. Right. But you can see is these are more reasonable numbers to manage rather than these big guys and these big ranges over here. If they were all big, that'd be one thing. We just measured in bigger units, but they're not. We have to be able to go across, and that's when we use that log scale. And if we're interested, let's just see here. We do have here. So first is here's the sound one, just so we know where it's coming from. Is it's in micropascals. So the softest sound a human can hear, 20 micropascals. The loudest sound is 2 billion there, and that's the launching. Maybe it's not the loudest sound, but the launching of a space shuttle is 2 billion micropascals. In that big range. I should bring up here is we do this sometimes when we look at over time some changes. One example is the stock market. It's changed by how much money is in there by so much that you could see that linear scale. It's a little tough to tell what's going on down here because it was such small change down in 1930s, 1935-ish. But if we go to the logarithmic scale, things get squashed up top a little bit, but we at least could get a bigger, wider view, and it's because it's just going over such big value changes over that time period, and it's why we use the logarithmic scale there. So be cautious when you're reading stuff. Sometimes they will do a logarithmic scale, and you have to pay attention to that. It's a little different. It's still on the y values or the log of what you think it may be there. All right. So that. Let's get the iPad back up there. So let's look at some examples. Suppose a patient receives 75 milligrams oral dose of a drug A at 10. let's say that's 10 a.m. Takes an hour for the drug to enter the patient's bloodstream. Her body metabolizes the drug at a rate of 8% per hour, and the drug manufacturer recommends giving the patient another dose when there are 15 milligrams left in her body. Okay. Well, I want to say here it takes an hour for the drug. This actually ends up coming out in the wash. All right, we put the drug in at a certain time, and we want to know so we're going to know what a function here. F of t equals milligrams in body at time t. Okay, here milligrams is the milligrams of some drug A. All right, so let's think about that. What happens? Let's forget about that hour it takes to go to enter the bloodstream again, because it's going to happen on the beginning and when you go to reduce it. So I think it's easiest we just pull that out of there. Now, let's see. We start with 75. All right. Metabolize the drug at a rate of 8% per hour. So let's see. Can you come up with that? What does that mean? It's a periodic. It's not continuous. So it's going to be 1 plus R rate R. So that's 1.08. And it's every hour to the T. Okay. Oops. What did I do wrong there? Not 1.08. That would be growth. This is decaying. It's the drug metabolizes. Another reason to say that it's leaving the system. So this should be 1 minus 0.08, which is 75 times 0.92 to the T. All right. And we want to know when our function, the question asks us, when is our function 15 milligrams? 92 to the T. And just because it's nice to look at some of the things we have, let me go over here. I'm going to put in a new function f of x. This for the 75 times 0.92 to the x. Okay, oh, well, let's go to home. Oh, somehow I lost that times, huh? There we go. So we know we want to go down here. There we go. There. Oh. 72. I see what happened now. Okay. Let's get this out of our screen. That's what it looked like. F of x. This is the amount of drug in the system. So what are we looking at? We want to know when is there. Maybe you want to see it up there where it crossed. That's the initial condition. That's 70. Oh, I keep on getting this wrong. Why do I do that? 75. Sorry. Good thing I checked that. We want initial condition time t at t equal to 0. It's 75 and it's decreasing exponentially. We want to know when it gets to 15, which is a little tough to tell. Let's see. This is 10, 20, 30, 40, 50. So somewhere around here. So it looks like it should take somewhere about 19, 20 hours, right? That's guessing in a way, or using the graph. We could use our algebra now. We know how to solve this. We first want to divide both sides by 75, okay? And 15 divided by 75 is, I don't have much time, so I'm just going to do it in here. 0.2. So 0.2, and this is when 20% is left, okay? So this is 0.92, all raised to the t. Now, even though our base is not e, we're still going to use the natural log of each side in order to get that exponent, or get that variable out of the exponent. And here we wind up with natural log of 0.2 equals t times the natural log of 0.92. Okay, remember that's using our power rule right there. Next up, we divide natural log of 0.92 as a number, so t equals natural log of 0.2 divided by the natural log of 0.92. And that comes out to be approximately, I don't know what that is, ln of 0.2 divided by the natural log of 0.92, and so approximately 9.3 hours, 19.3 hours. So that's what can it be? 36, about 5 hours and 20 minutes or something, right? 0.3 hours is a third of an hour is 20 minutes, so somewhere around 5. So not 5 hours. Somewhere around 5. I don't know. 5 a.m. at 5:20 a.m. Okay. The important thing is it takes 19.3 hours, and we add that to the 10 hours. So, oh no, I did that. 19.3 hours, right? That's how long it takes. Well, if we gave him the first dose at 10, when is that later? Oh yeah. 30. When's that going to be? 24 hours later, one way to do it. Anyway, 10 a.m. plus 20, say, or plus 19, that's going to give me 29, which is, what, 5, so about 5:20 a.m., okay? All right, let's see our next example. So here, we have the half-life of plutonium. Now, I'm going to stop this lecture here because it seems like I've talked more than I thought, and I'm at the 23-minute mark, and I don't want to make these too long. So I'll call this part 1, and we'll do applications of exponential logs part 2